Next up, velocity time graphs. The only type of graph that we've seen so far has been a position time graph, and we've learned what various shapes of those position time graphs represent: constant velocity, increasing velocity, acceleration, deceleration, whatever the case may be. We've also learned to deal with those graphs in terms of an analysis, how to calculate this value or that value or whatever. I'm going to show you a bunch of different shapes of velocity time graphs right now. Velocity time graphs means, of course, velocity comes first, time comes second. That means velocity will be on the y-axis, time on the x-axis, because it's always y versus x, right? This page should look somewhat familiar to you because it's the exact same shapes that we had for our position time graphs, but the meaning of these graphs will be different. If we have a position time graph that looks like this, that meant constant velocity. If we have a velocity time graph that looks like that, what do you think it means? What do you think this one means? Yeah, it's a constant acceleration. Look, the velocity is increasing. It can't be a constant velocity. It's an increasing velocity, but at least it's increasing at the same rate. So we're going to say it's a constant acceleration. If we had a position time graph that looked like this, it would mean the object is stopped. If we have a velocity time graph that looks like this, clearly the object isn't stopped. Look, there's a velocity. It's not zero. It's not stopped. So what's it going to be, Lewis? This one's going to be a constant velocity. If we had a position time graph that looked like this, we would have said that's a constant velocity, but in a negative direction, a constant negative velocity. This one's not a constant negative velocity. Look, the velocity is changing. So what's this one going to be, Stephanie? Good, a constant negative acceleration. Or you could say a constant deceleration. That would be fine as well. If we had a position time graph that looked like this, it would mean acceleration. What about a velocity time graph that looks like this? Yep. Yeah, it's still acceleration. But here we've got a changing acceleration. Specifically, it's increasing. So not only is it going faster, but the rate at which it goes faster is increasing. Does that make sense? The velocity is increasing, and the rate, oh, this is a mouthful right here. The rate at which the velocity increases. So we're going to say an increasing acceleration. Not just an acceleration, an increasing acceleration. You know what this is? This is like putting your foot on the gas pedal a little bit. What happens when you put your foot on the gas pedal a little bit? Do you speed up? Sure you do when you put it on the gas pedal a little bit, right? You're sitting at a stop sign. You put your foot on the gas pedal just a bit. You speed up. But then as you put your foot further and further and further down, not only do you speed up, but you speed up quicker and quicker and quicker. So that's what this is. It's like putting your foot on the gas pedal progressively further down. If we had a position versus time graph that looked like this one, that was a deceleration, a slowing down, right? This one's not slowing down. Look, the velocity is getting bigger. So what does that mean? What does that one mean? Jared, what's that one mean? No. Okay. Increasing deceleration. No, not quite. Yeah. Decreasing acceleration. Yes. So what does that mean really? Like that's kind of a decreasing acceleration. What does that mean? It's speeding up. Look, the velocity is getting bigger. It's speeding up. But as time goes by, it's not speeding up as quickly as it was before. The analogy there would be put your foot on the gas pedal. Okay? Put your foot on the gas pedal all the way to the floor. What happens? You accelerate very, very quickly. As you ease off the gas pedal, you still speed up, but you're not speeding up as quickly as you were when you had your foot on the floor. Make sense? Decreasing acceleration. Still speeding up, just not as quickly as before. All right. Those are good, I think, more or less. Let's take a look at how we might actually calculate something from a velocity time graph. Let's try to keep the position time graph and the velocity time graph straight. The shapes can be the same. A lot of stuff that I ask you is going to be the same, but the way we find it will be different. Here's my velocity time graph. Let's make the graph a shape like this. The first thing that I asked you on a position time graph was the instantaneous position, the position at one moment in time. You went up and over. If we want to find the instantaneous velocity, the velocity at one moment in time, we're also going to go up and over. How do you think you might find the change in velocity? Ryan, how do you think you might find the change in velocity? Let's say between now and now. Up and over again. So that's going to give me a velocity. No, I want to find the change in velocity over this amount of time. This one? This one? What are we going to do with that line, though? We're trying to find the change in velocity. Oops. Yeah. Right, we got a velocity. We got another velocity. Let's subtract them. The change in velocity is the difference between the two, right? So it's going to be up and over, up, oops, up and over, and then subtract them to get the change in velocity. Acceleration. You know, let's get rid of that second stage, actually. That might confuse you right now. Acceleration. There's two ways. Remember, the velocity on a position time graph was either the slope or v equals delta d over delta t. The acceleration on the velocity time graph is either the slope or, let's go back to the equation, delta v over delta t. Instead of delta d over delta t, delta v over delta t. Here's the one that's going to bug you a little bit. The displacement on a velocity time graph. This is the one that's completely different than anything on a position time graph. Oh, 3 of you think you know this? You guys remember this from Science 10? Aren't you supposed to forget everything once you leave grade 10 and have to learn everything new? Good for you guys. What is it, Haley? Yeah. The displacement is the area. Now, in this one, it's pretty straightforward to find that area because it's just a triangle. It'd be 1/2 base times height. But if you had a graph that looked like this, it'd be a little bit harder. Because look at this. We got, like, how do you find the area of that shape? Well, I break it up into a triangle, a rectangle, another triangle, and another rectangle. Calculate the area of all 4 of those things, and then add them up. Oh, here's one that's even worse. Let's get the area of the triangle. Let's get the area of the triangle. Let's get the area of the rectangle. But these two down here would be negative. So whatever area you got there, you'd consider to be negative. This one would be positive. You add them all up, same as you do over here. But these guys are all positive. 2 of these are negative because they're below the x-axis. On the handout that I just gave you, on the front of that handout, there's an example of velocity versus time graph, and you're asked to calculate 4 things. I want to go through that example now and leave you guys with the questions on the back of the page. What is the velocity at 4 seconds? Remember how to do that? Atlanta, you know how to do this one, right? The velocity at 4 seconds. Up and over. So at 4 seconds, we go up, we go over. It's 15 meters per second. The change in velocity over the entire graph. Well, the velocity at the beginning looks to be 3. The velocity at the end looks to be 33. 33 minus 3 is 30. Find the acceleration on this graph. There's two ways to find acceleration. There's the slope, or there's delta v over delta t. Which one do you want to use? Slope or delta v over delta t? Brian, what do you want to try there? Do you want to use the slope or delta v over delta t? Slope, okay. They're both the same, right? If you do rise over run, rise is delta v and run is delta t, but it's just two different ways of thinking of it. Okay, let's try the slope since that's what Brian wants to do here. Slope is rise over run. The rise from start to finish is 30 meters per second. The run from start to finish is, what is that, 10 seconds? 10 minus 0 or 10 seconds? 3.0 meters per second squared. And finally, the displacement. Not too hard of a displacement to find here. It's not just a triangle, though, so it's not quite that simple. There's a triangle, and there's a rectangle. The displacement is the area. The area of the triangle is 1/2 base times height, so it's 1/2 of 10. And the height of that triangle is 30, not 33. The triangle starts at 3 and ends at 33, so the height of that triangle is going to be 30. The area of the rectangle, it's a rectangle, so it's base times height. The base is 10, the height is 3. 30. What do we do with this 150 and 30? Yep. Nope, not 150 minus 30. Close. Charlie, what do you think you're going to do with that? Add them, right? Lewis, if that was below the x-axis, I'd make it a negative and subtract, right? But since they're both above the x-axis, we got to add those areas together. 150 plus 30 is equal to 180 meters. Yes. Yes, that's a good question. But the answer is yes. If you didn't hear that question, guys, because it starts at 3 meters per second, do we need to calculate the area of what's underneath it? Here's why the answer to that question is yes. If an object starts at rest and accelerates for 10 seconds, will it travel as far as if the object starts at 3 meters per second and accelerates? The one that's moving at 3 meters per second when it begins is going to travel further than the one that's at rest when it begins, right? It's got a head start. It's going to travel farther. Well, if we don't calculate this area down here, then it would be as if it started at rest. So we do have to account for everything. Everything between the line and the x-axis we have to calculate. Does that make sense, Lewis? The answer is 180 meters. Hey, I didn't ask you this question. Anybody have a thought on finding the average velocity? We'll give a special prize to the person who can tell me how to find the average velocity. No. Good idea, good guess. Yeah. Nope. That's acceleration, right? We want to find average velocity. Oh my goodness. Can't do this, eh? Nope. Good guess. This is good that it's taking you a little while because I'm still trying to think in my head what that special prize is going to be. I don't know what the prize is going to be yet, so keep going. Yeah. Okay, in this question, that would work. The change in velocity divided by 2, and that would work because it's a straight line there. But if there wasn't a straight line, that wouldn't work. So we don't want to go there, even though you're right for this graph. We don't want to use that method because it doesn't work for all the graphs. Does that make sense? Let's try to come up with a more general way. Do I get to avoid giving the special prize? It's a special prize, guys. It really is. I just have to figure out what it is. Yeah. Yeah. Displacement over time. We just got the displacement. It's 180. Time is 10 seconds. It starts at 3 meters per second. It ends up at 33. The average is 18 meters per second, which is exactly what you would have got, Brian, had you added 0 plus 33 divided by, no, sorry, 3 plus 33 divided by 2, right? But that only worked, your method only worked for this graph because it was a straight line. This works for all of them. Okay? All right. You got a worksheet to do, guys. Flip over the page. 4 questions, I think it is on that page. Yep. See what you can do.